Welcome to Badger Talks Quick Picks, which brings exciting happenings, resources, and talent from your UW flagship campus to the people of Wisconsin and beyond, demonstrating the power of the Wisconsin idea, one connection at a time.
Welcome to Badger Talks. My name is T.W. Huang. I'm Associate Professor in the EC Department at UW-Madison. Today, I'm going to talk about how we can make parallel computing easy and accessible using our research project, Taskflow. This is what I'm going to do for today's talk. First of all, we are going to understand the importance of parallel computing. Then, I will introduce Taskflow and show you how we can use it to easily program task graph parallelism. Next, I will showcase some real-world applications of Taskflow and conclude the talk. Let's first understand what parallel computing is. Traditionally, software has been written for serial computation. This basically means a problem is broken into a set of instructions that can run on one central processing unit, or CPU, the heart of a computer. These instructions are then executed one after another, and only one instruction can run at any time. On the other hand, parallel computing runs multiple instructions simultaneously by scheduling these instructions to different CPUs. So multiple CPUs can work together to solve the problem more efficiently. And you probably could already guess, parallel computing has advanced many of your application performance to a new level that is previously out of reach. For example, if you want to train a machine learning model using 40 CPUs running together, you can get 10x speed up. That is hours of saving using just one CPU. More importantly, modern hardware has been designed to run many things in parallel for performance reasons. For example, here I'm showing you an Intel Haswell microarchitecture, which was released in early 2013. This architecture typically comes with 4 CPU cores, and it has an integrated GPU to run graphics applications. It is based on a superscalar architecture that can issue multiple instructions at the same time per cycle. It also supports hyper-threading technology that allows a single physical CPU core to appear as 2 logical processors to the application. So the takeaway over here is, if you don't do parallel computing, you are not utilizing your hardware efficiently. However, today's parallel computing problems are very complicated and irregular. Here, I'm showing you a computational task graph of a GPU parallel circuit simulation workload. The task graph models a GPU operation in a task and the dependency between 2 GPU operations in an edge. As you can see, this computational task graph can be very, very large. In this example, where we are simulating NVIDIA's deep learning accelerator design that has 500 million gates, the resulting graph has more than 1,000 kernels and dependencies. Even with the state-of-the-art GPU from NVIDIA, it will take several hours to finish. This is another example of irregular parallel computing problem, where we want to parallelize static timing analysis, which is an important job in circuit design, using many core CPUs. The analysis algorithm is normally modeled as a task graph that propagates the timing values from the input of the circuit to its outputs. For large design, the resulting task graph can again be very, very huge, with more than 100 million tasks and 50 million dependencies. And turns out, parallelizing this type of irregular problem is not very easy because you have to deal with a lot of technical details, such as parallelism abstraction, concurrency control, scheduling efficiencies, and so on and so forth. And there's always this trade-off between what you want and the cost of that intent. You know, everybody wants simple, maintainable, extensible, and portable implementation. But each of that intent comes at the cost of a performance. So we really want a solution that can sit on top to help us manage these technical details as much as possible. Because developers really care how fast they can get things done. And by fast, I mean both performance and productivity. Now, I'm going to introduce our research project called Taskflow to help you overcome these challenges and show you how we can use it to program task graph parallelism. Taskflow is a general-purpose parallel programming system that helps you easily parallelize your applications using modern C++. And let's take a look at an example in our system, Taskflow. Suppose you want to do 4 things, A, B, C, and D. Each represents a function or a task. A has to run before B and C, and D has to run after B and C. When A finishes, B and C can start, and they can run in parallel. When both B and C finish, D can start. Now, to get a parallel execution for this task graph, using our project Taskflow, you only need about 15 lines of C++ code. You first define a Taskflow object and executor. Then you define 4 tasks in terms of C++ function object, A, B, C, and D. And then you use the precede and succeed method to relay the dependencies among A, B, C, and D. When a graph is constructed, you submit it to the executor for execution. We call this model static task graph programming because the construction and execution of the task graph are separate from each other. You define the task graph first, and then you submit it to our system for execution. More importantly, at this moment, I believe most of you, even though you do not have that much programming experience, can fully understand what this code is doing. That is the power of our research system. In addition to static task graph programming, Taskflow also supports dynamic task graph programming, so you can use it to solve problems in a more dynamic environment. Using the same graph as example, you can create a task from a C++ function object using silent dependent async or dependent async if you would like to perform task-specific synchronization in your graph. When you create a dependent async task, you can specify arbitrary dependency on previously created tasks. For example, when creating task D over here, I pass B and C as the last 2 arguments, indicating that task D cannot start until both B and C finish. More importantly, when you create a dynamic task, the runtime will start its execution immediately whenever its dependencies are met. So the task graph construction can overlap with task graph execution, giving you more performance advantages. Now, I'm going to showcase some real-world applications of Taskflow. We have applied our system Taskflow to successfully parallelize an important application in circuit design, that is static timing analysis or STA. And most STA algorithms require us to propagate the timing values from the input of the circuit all the way to the output of the circuit. And the computation is very, very complicated and irregular. For the given circuit, we use our system Taskflow to derive a timing propagation task graph, where each task represents a particular timing propagation function, and the edge represents task-to-task dependency. Then, we run the Taskflow to evaluate and report violated timing path in parallel. We have actually implemented this task parallel propagation in an open source project called OpenTimer, or V2. As you can see from the result over here, we can clearly see the advantage of Taskflow. No matter how many CPU cores you use, there is always a consistent gap between Taskflow-based and non-Taskflow-based solutions. And that is because our system Taskflow allows you to more asynchronously parallelize the timing propagation using just a few lines of C++ code. At the time of this presentation, Taskflow has a weekly download number of 7,000 to 9,000. It has grown almost 3x over the past 5 years. We have people using Taskflow for quantum computing, bioinformatics, computer graphics, embedded system, scientific computing problems, and so on and so forth. In today's talk, we have understood the importance and challenges of parallel computing. We have also introduced our parallel programming solution, Taskflow, and show you how we can use it to program both static and dynamic task graph parallelism easily and quickly. Finally, we went through some real-world applications of Taskflow. Finally, I would like to say thank you to those who are using the project Taskflow in their daily job. Taskflow has been used by a growing number of people from both academia and industry. If you are interested in learning more about Taskflow, please check out our project website at taskflow.github.io. We are very open to collaboration. Thank you very much. That concludes my Badger talk.